In this video, I'm going to talk about a block diagram. In the previous video, I talked about transfer function. So the transfer function basically talks about the relationship between the input, u sub t, and the output y sub t. Not here, not in the time domain, actually in the s domain. So instead of studying the relationship between ut and y sub t for a given control system, we are looking at the relationship between the input u sub s, which is a Laplace transform of ut, and y sub s, which is a Laplace transform of y sub t. So in particular, the transfer function g sub s is defined as ys divided by u sub s. So ys is a Laplace transform of the output. U sub s is a Laplace transform of the input of u sub t. Here, there's an assumption here is the initial conditions, the initial state is 0. Okay, that's the assumption we need. Okay, now this one actually can be used to quantify the relation between the input and output, because actually initial state has impact on output, but the impact of the input on the output can for the control system, let's say represented by ODE, can be fully captured by the transfer function. Okay, so this is for one block. You can see that in my previous video I talked about this is sort of one block. You can also combine blocks together to build a complex system. Okay, so the key concept is called a block diagram. Okay, so before talking about a block diagram in more detail, I'm going to talk about what's the definition of block diagram. Block diagram is a graph representation of the cause and effect relationship between the system variable in the S domain. Okay, so you sort of, I want to emphasize a little bit about the cause and the effect. You can sort of consider this as the input and output in our case. So what's the input impact on the output? Okay, between different variables. We talk about input and outputs. Of course, here I want to emphasize here is in the S domain. So it's just directly connected to the transfer function I mentioned in the previous video. Okay, so now I'll give you an example about what this means. Okay, so as I mentioned here, the block diagram is a graph representation of the cause and the effect relationship between signal variable in S domain. So we can define system variables actually. So you just use that one to define the relationship. So for example, in the previous video, I talked about the transfer function for between the V sub 1t and the V2t for RC circuit. So R resistor, C is the capacitor. So from my previous video, the relationship between the system variable, if I use the V1s and V2s here, because the definition says it must be in S domain, so the variable must be in the S domain. So I have V1s. So V1s here is the Laplace transform of V1t, and this guy is just Laplace transform of V2t. Okay, so the relation between the V1s and the V2s can be described by C divided by Rs plus C, which means I have V1s times C over Rs plus C is equal to V2s. So this is the between variable. You can see the between variable and this variable, the relationship carried by this. Also you describe in S domain. So yeah, this is a block diagram. It talks about one block basically. So the other one is we could also have the block. We can put the block together basically. Let's say here, if I give you a system described by, let's say U1s here, is already given in the S domain. So you could have a U1t, but we already give the Laplace transform of the U1t. This UT, sorry, is UT. I already give you a Laplace transform, so you get this U1s. And the output is y sub t, and of course I already say Laplace transform given by y sub s. So I could have multiple blocks. Okay, here the reason I call it multiple blocks because here I can sort of introduce an intermediate variable ws. Okay, because the block diagram just talk about relation between the system variables. I can say I have ws is a variable just over here. So this is my the output over here. This is W. You can consider in the time domain. This is WT. So whatever signal I got over here is WT. So when you apply Laplace transform, you get a WS. So if I talk about the relationship between the system variable of WS and US, so it's described by S divided by S plus 1 because that's my transfer function, which is defined by the transfer function. Similarly, I have YS divided by WS is given by 1 over S plus 1. This because this is also the transfer function. So this also is a blocker because it categorizes the relationship between the YS and WS. So as you can see from here, you can sort of see that the block, you can have multiple blocks to describe a system. Okay. One nice thing for when using block, because you can combine them to make it simple. Okay. So I sort of, when you have this one, you sort of can see I can combine the blocks. You sort of put, well, when I want to find a relation between U sub S, if they're sort of connect like this, oh yeah, I can just put them together. Okay, just do the product. Okay, the reason I can do that is because I do WS divided by US times YS divided by WS, because WS will cancel out, so I have YS divided by US. So you sort of can see the relationship between this guy and this guy, the two variables, like I mentioned here, it just product these two. That's why I can put them together. Okay, so the nice thing when we use block diagram is we can use a multiple diagram using their relation to describe a complex relationship for a control system. Okay. So next I'm going to talk about one important property we're going to talk about is called a transformation of block diagram transformation. The reason we do that is if I give a complex system, typically we want to figure out what's the relationship between input and output. For example, I have multiple very complex system. Well, how do I give a block diagram? The block diagram are sort of connected. Okay, so it could be very complex. How do I simplify their relationship between this block diagram such that I can get the final transfer function? So that's the goal. Okay, so the key technique to simplify the block diagram or transform block diagram so that we can find a transfer function for a complex control system that are represented by multiple diagrams with complex relationships is called block diagram transformation. Okay, so this is the approach we're using. So here's the definition of block diagram transformation. So block diagram can be equivalent transfer from one format to another one, which is called a block diagram transformation. The reason we do this one is to find the transfer function for a complex system composed of numerous blocks with complex relationship. So that's the reason we want to use a block diagram. Okay, so we want to figure out, hey, and when they have very complex relationship, we have numerous blocks. How do we simplify and we can find the transfer function? So that's the main goal. We introduce a block diagram. So before I talk about how do we simplify, I want to talk about what kind of relationship we're talking about. So what kind of relationship we're talking about. So we can summarize it in several different cases. We talk about each case, how do we do the transformation. Then hopefully those cases can help us find a transformation for a complex system composed of a different type of relationship. So that's what I'm talking about next. So I'll give an example. I'll first talk about different cases, different relationships, and how do we do the transformation. And then I'll talk about, give a few examples talking about how you can use this cases I mentioned below and to simplify the system to find the transfer function. Okay, so let's start with the first case. The first case called combined block in Cascade. Okay, this is exactly what I mentioned over here. This is called Cascade. You can also say it's Cascade relationship, which means you sort of have this. You have, if I give you, say, x1s is my first one, so it goes through one transfer function g1s, and it gives us output is x2s. It goes cascade, it's kind of chain, go to g2s, and the output is x3s. Okay, So this one can be equivalently written as, can be transferred into another format, which is just to combine the product of these two together, which is quantify relationship between x1s, x3s. So this is called cascade. It's fairly easy to understand from what I mentioned over here, okay? Alright. The second case is I'm moving a summing point behind the block, okay? For the control system, we typically have the feedback, either positive feedback or negative feedback, okay? So important case is we need to probably have to move the summing point behind or in front of a block, okay? The second case said, how do we move a summing point behind the block? So originally the summing point is a front of block, for example here. So it means, okay, I have two inputs. Here I already dropped all the S. I have dropped all the S. I should have x1s, x3s, x2s, and g sub s. I dropped that for simplicity, okay? So if I input x1, x2, and they could have a plus, and then go over this g transfer function, then the output is x3, okay? So this one can be equivalent written as, you move this one to the sum point after the transfer function over here, after block. So when you do that, you sort of want to introduce this g over here. The reason you can do that is, the reason that you have to introduce this g is, if I calculate this x3, so I sort of have, so if I do this one, so this one x1s, x2, okay? So this right over here is x1 plus or minus x2, okay? And the transfer function is g because relation between this one is, so I have x3 divided by x1 plus or minus x2 is g, which means I have x3 is x1 plus or minus x2 and times g, okay? So the plus or minus determined by this sign. So this one can further be written x1g plus or minus x2g, okay? That's the reason you do over here. So x1g go here, okay? This one you basically here, this one point here is x1 times g, and this is x2 times g, okay? So depending based on the sign over here, it's plus, we have plus, it's minus, we have minus, so it's equivalent to the original x3 we computed over here. That's why you have to introduce this g. Don't forget that we must have a g over here, okay? So similarly for case 3 is we're moving a pickup point ahead of block, okay? I think there's something, okay. For this case, I have to move this point. For example, I have feedback. I want this one feedback to the previous beginning, okay. Well, this one says I have to, so here, if I do the calculation over here, so my x2 goes here, right? So if I go over here, okay, you want to do over here, so I have to, so I can let the x2 keep on going, okay, I can let it keep going. If I want to move this one over here, I have to time g. The reason I'm doing that is because here x2 is given by, this x2 is given by x1 times g, okay? So if I would only use this one, so I only have x1, okay? So I must have time g to get an actual x2 as a feedback. Otherwise, I just have x1 as feedback. So I have to add on this g, okay? So equivalently, you have to add on the g, so that x2 is x1 multiplied by this g, okay? The next one is moving a pickup point behind a block. Pickup point behind the block. This is summing point behind the block. This is pickup point. Don't get confused about it. So okay, emphasize over here. So this is summing point move behind. This is the pickup point, and the pickup point ahead and behind, okay? The next one, I'm going to move a pickup point behind the block, okay? So here, let's say I'm going to have this one as my feedback, sort of. I have x1 goes back to a certain place, okay? If I'm going to do here, I'm going to move this behind this one, so I have to do this one. This has to have 1 over g, 1 over g. The reason here I have 1 over g is because here x2g, here x2 is x1 times g, okay? If I only have this guy as my input, this will just x2, so it's not equal to x1. If I want to have the same x1 pickup point, so I want to time 1 over g such that I want it x2 time, so x2 time 1 over g is x2 because x1g time 1 over g, so it becomes x1. So this will pickup point, it still become x1. Okay, so this is not right. Apparently here this is not right. Okay, this is case number 4. case number 5 says moving a summing point ahead of block. Okay, this is also summing point ahead of block. Okay, so originally, okay, I have x1 goes through a transfer function of g, and this plus, and then there's another x2 input is a plus or minus, and the output will be x3. So if you calculate this one, you get x3. So this point, if we do calculate over here, so this point will be just x1 times g, because that's a transfer function is g, right? So x3 will be just equal to x1g plus or minus x2, depending on what the sign I have over here. If this is plus, this is plus. If this is minus, this is minus. Okay? So if I move the sum in front, okay, I have to add on this 1 over g, okay? The reason that's the case is, if I do over here, so this point here is x2 times 1 over g, okay, because of transfer function. So this point will be the sum of these two. Of course, it could be plus or minus. It's x1 plus or minus x2 times 1 over g. Okay, then this x3 will be just x1 plus or minus x2 1 over g times g, which is x1g plus, let me see, x1g plus or minus x2, which is the same as this over here. Okay, that's equivalent. That's why we have to have this extra transfer function over here. The last case is called eliminating a feedback loop. Let's say we have a feedback loop. We have input x1, output x2, and it's plus or minus, and there's feedback from x2, and with this is the h is a transfer function, this is another transfer function of g. This one, the loop, the feedback could be positive or negative. Could be positive feedback or negative feedback. So this one can be written as x1, x2 go over to here. The transfer function is g divided by 1 minus or plus gh. Here's a minus or plus. If this is a plus, okay, so I'm going to here, this is a minus over here. If this is a, use different colors. If this is minus, so going to here, I'm going to have plus. Okay, that's why it's opposite. Okay, why that's the case? Why that's the case is it's change of sign, or why that's the exact relationship between x1 and x2. So okay, we can do the calculation over here. So if I calculate this, this is x2. So this point here is x2 times h. Okay, so this point will be x1 plus or minus x2h, basically. Okay. So I have, so this guy point actually is x1 plus or minus x2h times g. Okay, so apparently this dot at any point over here is the same as the output x2. That's why this point will be equal to x2. That's why I have over here, okay, x1 plus or minus x2 times h times g is x2. So we just do the multiplication. So x1g plus or minus x2gh is equal to x2. Okay, I'm doing one more step. Okay, get a little bit complicated. So this one I have x1g equal to x2. This is because I moved this one to the right hand side. So plus or minus become minus plus x2gh. So this is x2 1 minus plus gh. Okay, so I have, if I do over there, I have x2. So I do move x1 to the left hand side, right hand side, move this whole thing to the this hand side. So I have x2, x1 on my right hand side. My left hand side will be g divided by 1 minus plus gh. So which is, this is what I have over here. Okay, so that's how to eliminating a feedback loop. Okay. All right. As I mentioned at the very beginning, the whole point that we do all the relationship, we understand all those sort of relationship is to do what? Is to use the sort of different cases to simplify my complex block diagram, so I can find a transfer function for a complex control system composed of numerous blocks with some complex relationship. Okay, so I'm going to show you two examples, show you how to use these 6 different cases to simplify a complex control system into a simple one, so you can find the transfer function. Okay. All right. Let's first start with a simple one. Okay. So the first example is we want to use aforementioned properties or cases to determine the transfer function of block diagram or complex control system. All right. So here's the example I give you. First one, I give input R sub s, output is Y sub s. So here I do have a feedback loop, sort of a negative feedback. And also here I have G1, G2, and G3. That's sort of a cascade sort of relationship. Okay, it's a combination. It's not just the previous one of the previous cases. It's a combination of the previous cases. The whole point is what is if I want to find out what's the transfer function between R sub s and Y sub s. What's the relationship between S and Y sub s? Okay, how can we do that? All right. So this transfer function now actually what we can do is we can use the property. Because this is a cascade, okay? Cascade, of course, in the previous cascade, I only mentioned we have 2 blocks right over here. Of course, you can have more. If you do have more, you just have more multiplication of different blocks. That's it, transfer function. So essentially, what I do is, here is, well, I have cascade, 3 of them. So I can put them together. So basically what I do is I can just eliminate this 3. Let's do that one. I can eliminate 3. Do a different color. Eliminate 3 and replace this 3 by a big block. This block is just G1, G2, and G3. That's it. Okay, I dropped the S. There should be G1 S, G2 S, G3 S, of course. Now after that, we only have 1 block, and then we have here I'll probably have a feedback loop. Okay, so the difference between this is the case. For the cascade is case 1. For the feedback loop is case number 6. How do I eliminate the feedback loop? So the difference between here and the previous one over here is I don't have G over here. The G becomes G1, G2, G3. You can consider the difference. So naturally, I just have to replace G by G1, G2, G3. That's it. Of course, this is negative, so it becomes plus according to relation over here. So this becomes transforming is Ys over Gs is G1, G2, G3 divided by 1 plus G1, G2, G3 times H. The only difference here, I sort of replace G by G1, G2, G3. So you sort of suppose this is G in my case number 6 over here. So this can be equivalent written as here is G1, G2, G3 divided by 1 plus G1, G2, G3 times H. That's it. Okay, so this is a simple example. Okay, so next I'm going to show you a little bit more complex example. It can be a little bit more complicated. Involve different cases. I'll go one step by one step. Okay. All right. So in this example, I have complex situations. I have R sub s. Still, the input is R sub s, and output is Y sub s. Okay. So the relation is really complex. So it goes through a feedback. And from the output feedback, and it goes through a transform G. It goes to another feedback. The feedback doesn't come from the Y output, coming from here. Go to the feedback, then goes to G2 and go to another feedback. This does come from the output, and then go to another one G3, then go to G4, and so on and so forth. Also, you cannot consider this as cascade because you have a signal output, right? If you put them together, you don't know where this one will feedback to over here. So that's why. It's really complex. Relationship is really complex. So how do I find? So my goal is still what is the transfer function of Ys over Rs. So this could be a really complex control system, but we still want to find the transfer function. So how can we do that? Assuming here, of course, I know G1, G2, and G3, and G4. I also know H1, H2, H3, and H4. Of course, this I'll have S. I ignore S for simplicity. Okay. Alright, so let's talk about how we do it. Okay, so the first thing first, okay, we don't know. You cannot do this loop as well. Of course, you cannot do the cascade loop. You cannot do this one over here. It's become really complex, right? So the reason here I start with this block. So the first part is there any way we can move this one to the right hand side? Move this one to the right hand side. The reason I want to do that is because I can do cascade basically, right? Then I sort of can do the loop, right? So one sort of idea is I want to move this one to the right hand. I move is like this one for case 2. I move feedback, move a pickup point behind the block. This is what I want to say. I want to move a pickup point behind the block, because if I would be able to move this one behind, pickup point behind that, I can consider 2 as a cascade. Okay, so first I do, hey, let's move this one, case 4, move this one, the pickup point behind a block. Okay, so originally, if I look at the case 4, when you move this one behind a block, you have to time the inverse. You have to give add an extra block, which is 1 over g. Okay, so of course, because this is 1, you do 1 over g. If this one you have an h, so you here you have h over g. Okay, so what happened over here is, if I want to move the block, move the pickup point behind this block, so I have to do the original block whatever I have, divide by this g4. Okay, so the reason that's the case, because if it's considered this signal, this is just let's say this is whatever I call it, e sub s, for example. So this point will be e sub s times g4. Okay, so if you divide by the original, because the original one, if you took a look, original one will be directly e sub s, right? Pick a point. Now if you do times g4, then divide by g4, so the feedback doesn't change. It's still e2 es. Okay, so that's why it's h2 divided g4. The reason I'm doing that is because I want to move the pickup point so that I can consider that as cascade. So next step I'm going to do cascade. Okay, cascade of this two. Okay, so I'm doing a cascade of this g3 and g4. Okay, so I'm doing cascade. Cascade is I put them together, so that when a cascade means, oh, I can put them together, g3 times g4. Okay, so this is case 1, cascade. Okay, this is pretty straightforward. So next time is, well, I can do a loop, a closed loop, because what I can do is I can do this. I can do this one feedback loop, because every point on the line they mean the same signal, because there's no transfer function, anything like that. So you can put this one backwards like this. Of course, you can do in the between whatever we want to do. Okay. So once you do that, you can consider this is just a loop. This part, if I do this part, this kind of just a loop is a positive feedback loop. So this is the way how we can simplify this. Okay, this is just, if I do the feedback loop, if I look at this one, okay, if I look at the feedback loop over here, is g divided by 1, because it is a positive feedback, so it's a 1 minus gh. So this is a, if you look at over here, so because g is, you can say g as g3, g4, so it's g3, g4 divided by 1 minus g3, g4, h1. Of course, this is h1 over here. The reason I have this minus sign, because this is a positive feedback. Okay, so I have g3, g4 divided by 1 minus g3, g4 times h1. Okay, now naturally I still have a cascade. Okay, let's do this one again. So cascade, so it just this two multiplication of these two. Okay, so I just put them together, g2, g3, g4, and the denominator will be still the same, 1 minus g3, g4 times h1. Okay, now we do one more thing, because this is a feedback again, loop again. Although it go up, it's still a feedback loop. You can put it down if you want to, but it's a feedback loop. Okay, so here, this is a loop, right? Because it's a feedback loop. Okay, of course I can move this one. If you don't see, you see this pick point doesn't make sense. You can move this one to this right hand side, because it doesn't matter, every point on this line means the same signal. You can just pick up on here. You move the computer from here to here, doesn't change anything. Okay, so here I have to consider what is, this is the negative feedback, so I consider this whole thing as my g, this whole thing my h. So it's negative feedback, so it's a g divided by 1 plus gh. Okay, of course I replace g by this whole big stuff. Okay, so g is replace the whole thing over here, divided by 1 plus g is this big block, h is this block, so do it over here. Okay, so when I do the simplification, I'm going to do some simplification, I get this. Okay, you can do a simplification. You just times the denominator by 1 minus g3, g4, h1 times g4. Okay, you times this one also by the same 1 minus g3, g4, h1, g4. Okay, now you get this. You come up with, you get this, the final answer, the answer over here. Now it's become simple again. I just do another cascade. Okay, cascade is again, okay, I just do time g1. Okay, g1, g2, g3, g4. Just time g1, this whole block by g1. That's it. Okay, now I have final one is a feedback loop. Okay, so you sort of consider this whole thing as G, this guy as H. Okay, so because this is negative feedback, you have G over 1 plus GH. So I do the same thing. Okay, this is G divided by 1 plus G times H. H is H3, so I time H3 over here. So if you do the simplification over here, you do G1, of course, the same way. You time G4 minus G3, G4. Let's say I call this one, this guy, denominator, it calls D over here. You just time D over here, this time D, the whole thing times D over here. That's it. You can do the simplification. Now you get this final answer over here. Okay? Right. So the nice thing I want to emphasize over here is, although the original system here is quite complex, because each G1 you probably can have a very complex G1, G2, and G3 and G4. So this G1 is, you can sort of consider this G1 as ODE1. Okay, then you do input output. So this is very complex or even already. Of course, this G2, G3, G4 that can be very complex, and the relationship, of course, the H1, H2, H3 can also be ODEs. So their relation is really complex, and really complex over here. And it's almost impossible in practice for you to figure out the relation between the, if I talk about this R sub t and Y sub t in the time domain, it's almost impossible to figure out the relation between R of t and Y sub t directly, because it's really hard to say. However, if I'm using the S domain and divide it into blocks and try to quantify the relationship using block diagram, I can follow the step I mentioned here and try to figure out the relationship between the input and output, of course in the S domain, S and the Y sub S. Okay, the nice thing here is this one can be complex. Of course, this one still can be complex. However, if I give you the input, let's say I give you input R sub t is, let's say t, okay? What you can do is I can do apply a Laplace transform, so guess R sub s. So this transfer function I already figured out. This is already I figured out transfer function time. So I can do this one transfer function. It's already determined by this. It's a whole complex stuff. I can figure out my Y sub s. Then I can do the inverse Laplace transform, try to figure out yt. Okay. So if I don't use the approach, I directly look at the differential equation sort of like this. It's almost impossible to find the output if I give it input. So that's the beauty of the block diagram.